Central limit theorem is an important theorem in statistics with wide application. If you remember the sampling process, we have a population that we don't know much about. We don't know the parameters of this population, such as its average mu and standard deviation sigma. We do not know the size of this population, and we do not know the distribution of this population. To study this population, we take a random sample. For the sample, we can compute its statistics, such as x bar, which is the average, and s, which is the standard deviation of the sample. Then these are going to be used as an estimation of the population parameters. Although we do not know the distribution of the population, however, given circumstances, we can actually approximate the distribution of the random variable x bar, the sample means, using the central limit theorem. Let's see what central limit theorem states. Consider any population of observations with mean mu and a standard deviation sigma. When n, the size of the sample, gets large enough, more than 30, the distribution of the sample means will become approximately normal, no matter what the shape of the distribution of the individual values in the population is. So x bar, the sample means, would follow a normal distribution with an average of mu and a standard deviation of sigma over a square root of n. When we have the distribution of x bar, the sample means, we can do a lot of things with it. For example, we can find probability, we can actually develop a confidence interval later on, and that's why this is very important theorem. If the population follows a normal distribution itself, then for any sample size, no matter if it's greater than 30 or not, the sample distribution of the sample means will also follow the normal distribution. So for the central limit theorem to be true, when we take a sample, the size of the sample should be greater than 30. If this is true, then x bar, the sample means, would follow a normal distribution with an average of mu and a standard deviation of sigma over a square root of n. But if the population follows, if we know that the population follows a normal distribution, then we do not need this requirement. Let's see how central limit theorem came about. So the central limit theorem states that no matter the distribution of the population, the distribution of x bar, the sample means, would follow approximately normal distribution given that its size is greater than 30. So suppose we have these different distributions for the population. As you see here, the shape of this distribution is very different from each other. Then we take random samples from each of these populations. For example, we take a random of size 2, only 2 values from or 2 observations from each population. The shape or the distribution of x bar for these samples is as follows that you see here. None of them look like a really normal distribution. Then we increase the size of the sample. So for example, we take a larger sample, a sample of with 6 observations. You see that a dramatic change happens here. The distribution becomes more symmetrical and normal shaped. Then again, we increase the size of the sample to, for example, 30. So at 30, as you see here, all of these sample distributions, sample means distribution, are symmetrical and bell-shaped, which is approximately the normal distribution. Let's see an example. Suppose a population's mean is 8. That means mu is equal to 8. And its standard deviation is 3. So sigma is 3. Now suppose we take a random sample of 36 observations from this population. What is the probability that the sample means is between 7.8 and 8.2? So what we are looking for is the probability that x bar, sample means, is between 8.2 and 7.8. So although we do not know the distribution of the population, because the size of the sample is 36 and 36 is greater than 30, so according to the central limit theorem, we can actually use the approximate the distribution of the sample means distribution, x bar, would follow approximately a normal distribution with an average of mu, which is 8, and a standard deviation of sigma over the square root of n, which is 3 over the square root of 36. So let's see the solution for the example. Although the population is not normally distributed, but because we can use the central limit theorem here, because n is greater than 30, so we can approximate the distribution of x bar as normal. So the distribution of population is not known. We don't know what the distribution it has, but we can use the central limit theorem to approximate the distribution of sample means or x bar, which follows a normal distribution. So x bar would follow a normal distribution with an average of mu and a standard deviation of sigma over a square root of n. So sigma of x bar would be sigma over a square root of n, which is 3 over the square root of 36, which is 0.5. So this is 0.5, and mu is 8. So this is 8. So now we have the distribution of x bar or the sample means. Now we can find the probability that the question is asking for. So what we are looking for is the probability that the random variable x bar would follow between 8.2 and 7.8. To find this probability, we can use the probability density function, if you remember the complex problem, the complex formula, and then do the integral here, which is going to be from 7.8 to 8.2 f of x bar d of x bar. And f of x bar would be the probability density function of normal distribution. Or we can go with the easier or old way, which is using the z distribution, or we can actually use Excel. So right now we want to use the old way, which is using the z distribution. So we need to convert this to z distribution. This would be equal to the probability of z less than the z score of 8.2 and greater than the z score of 7.8. So this way we have converted the distribution of normal x bar to the standardized normal distribution of z. So now we go to the z table and find these z distribution values, and then we can compute the probability. The z score of 7.8 is negative 0.4, and the z score of 8.2 is 0.4. So if you look at these in the z distribution, you can find this probability, which is equal to 0.3108. Or you can use actually Excel to do that. And that would be using the norm.dist of 4.4 subtracted by the norm.dist of negative 0.4. Let's do a practice problem. The annual income for independent sales representatives in US is right skewed, with an average salary of $144,300 and a standard deviation of $32,450. We have taken a sample of 36 independent sales representatives. Find the probability that a sales representative's salary exceeds $126,000. So please pause, work on this problem, and then come back to see the solution. Right, let's see the solution. So here we have a population of independent sales representative in US. We know that the distribution is right skewed, but we don't really know the distribution. We also know the average salary, which is $144,300. Also, we know the standard deviation, that's $32,450. What we want to do is we want to find the probability that a sales representative salary would exceed $126,000. To find any probability, you need to know the distribution. But we don't really know the distribution of X. X is just a sales representative salary, it's a random variable. If you pick someone from the population, what would be the chance that his or her salary would exceed $126,000? Well, actually, the answer is we don't know. It's unknown because we don't know the distribution of X, which is the independent sales representative salary. So since we don't know the distribution, we can't really find the probability. And that's the solution to this question, the answer to this question. Part 2. What is the probability that the sample mean would exceed $142,000? So please pause, work on this problem, and then come back to see the solution. All right, let's see the solution. Although we do not know the salary distribution of the sales representative in the population, the question here asks the sample mean would exceed. So the question asks, what is the probability that the X bar, the sample means, would exceed $140,000? So do we know the distribution of X bar here? We don't know the distribution of X, but we do know the X bar distribution, the sample means distribution, because we can approximate it using the central limit theorem. N here is 36, which is greater than 30. So we can use the central limit theorem. The central limit theorem says that X bar, the sample means, would follow a normal distribution with an average of mu and a standard deviation of sigma over square root of n. Mu is $144,300. Sigma of X bar, the standard deviation of X bar, or the standard error, is sigma over a square root of n, which is $5,408. So X bar, the sample means, would follow a normal distribution with mu and sigma of X bar. Now that we have the distribution, we can find the probability. So the probability that X bar would exceed $140,000 is, we can find it using the Z distribution or using Excel or using the probability density function and an integral. So here we're going to go with the Z distribution. So we're going to convert this to the Z distribution probability. So that would be Z greater than the Z value of 140,000. The Z value of 140,000 is negative 0.79. And the probability that Z is greater than that is 79%. So the probability is 79%. Let's do a quiz. True or false question. One of the things that the central limit theorem tells us is that about half of the sample means will be greater than the population mean, and about half will be less. Please pause, work on this question, and then come back to see the solution. All right, let's see the solution. So the central limit theorem tells us that if we don't know the distribution of the population, but we know that the size of the sample is greater than 30, then the distribution of X bar, the sample means, would be approximately normal with an average of mu and a standard deviation of sigma over square root of n. And if you actually plot the distribution of normal for this, it would be a symmetrical shape. If you remember, for the normal distribution, the mean would be equal to the median. So mu is also our median. And median means that half of the data. So mu is also equal to the median. That means that half of the data on the left, half of your sample means is less than mu, and the other half is greater than mu. So this means this question states the right proposition. Next quiz. When sampling from a population, the sample mean A will likely be different from the population mean, B will be closer to the population mean as the sample size increases, C will likely be equal to the population mean if proper sampling techniques are employed, and D will typically exceed the population mean. So please pause, work on this problem, and then come back to see the solution. All right, let's see the solution. Let's go over every one of these options to see whether they are true or not. So we are sampling from a population. The question is about sample mean. That means we take a sample, we want to see X bar. This is not the random variable X bar. This is just X bar, which is the sample mean, the average of a sample. All right, let's see option A. X bar will likely be different from the population mean. So here we are comparing X bar with mu. And if you see and remember from the example that we had, X bar usually is different from mu. In fact, if the size of the sample is greater than 30, then we can use the central limit theorem, and X bar, the random variable X bar, would follow a normal distribution, as you see here. And this is mu, the average of X bar. So half of the distribution, half of the sample means their average would be greater than mu, and the other half would be less than mu. So most of the samples, the average would be different from mu. So A actually is true. B, the sample mean will be closer to the population mean as the sample size increases. All right, so to answer this question, again, suppose that n is greater than 30. It could be less than 30, but just for the sake of this example, suppose that it's greater than 30. Or if it's actually less than 30, we're going to increase it to become greater than 30. When it's greater than 30, then the sample mean X bar would follow a normal distribution according to the central limit theorem. That means that it would follow a normal distribution with an average of mu and a standard deviation of sigma over a square root of n. So if you look at the standard deviation of sample mean, it's divided by n, the size of the sample. If n increases, then sigma over a square root of n, this value becomes smaller and smaller. For example, suppose n is 30, and compare that with n equal to 60, for example. So sigma over a square root of 30, is this bigger or sigma over a square root of 60? Well, the first one is bigger, because when you make the denominator greater, then the value becomes smaller. So B is also true. Let's go to C. The sample mean will likely be equal to the population mean if proper sampling techniques are employed. This means that X bar would be equal to mu if we use a proper sampling method. This is actually not correct because the sampling technique is irrelevant here. It doesn't really matter. No matter what technique you use, usually X bar would be different from mu. So C is false. Part D. The sample mean will typically exceed the population mean. Well, this says that x bar is greater than mu. Well, this is not true either, because in terms of our central limit theorem here, which when n is greater than 30, half of the samples, the average is greater than mu, and half of the sample, the average is less than mu. So D is also not correct. So the two only options that are correct, the two only choices are A and B.